So in the last class, I told you, there has been some gap, but I told you a few things how we apply these concepts to the what you have learned about IR and Raman. You applied in understanding the molecules. Hmm. So the the application part of this, after learning the fundamentals of IR and Raman, this is what you have to do. You have to identify. You should be now able to, given a spectrum, you should be able to identify what are the features, what are the bonds present, what, and so typically that I told you a few things. So starting from here, if I may. So this is the basically regions of interest whenever you are dealing with this mid IR region. 400 to 4000 cm inverse is the most widely used in spectroscopy. Whether you are organic chemist, whether you are inorganic chemist, anybody, this is the region that will help you. Okay, and these are practically, it is easier to analyze this spectrum, practically easy in the sense that when you carry out the measurements, you can easily do that with the available tools. Going into far IR requires change of the optical window, so that again becomes slightly difficult. So usually by what we do is by KBR pellet method. So the range in that KBR window, KBR is transparent in that mid IR region. So it is widely available and it is useful for doing. The other method is, which is getting now more popular, is that ATR accessory. So the FTIR that we have got installed in our lab has both the options. You can do in the KBR pellet mode, that is सो ऑप्टिकल विंडो कैसे सिलेक्ट करते हैं, ये सब आपको तो पता ही है, खैर वो इंस्ट्रूमेंटेशन का पार्ट है, वी आर नॉट, आपने सेकेंड सेमेस्टर में पढ़ा ही होगा, दैट इज, बट समहाउ दैट रिलेट्स कि व्हाई वी आर फोकसिंग इन दिस रीजन. ये ज़्यादा इजी भी होता है ऑलमोस्ट, क्योंकि even a metal compound, that coordinate compound we are discussing, it is metal and ligand, and you mostly observe the vibrations of these ligands, which are organic moieties or something uh, like that. They will appear in this range. So observing them, you can talk about many things about strength of the bonds uh, by looking at the shift in the frequencies of the ligand. We analyze the metal, how strong the metal ligand bond would have been, or things like that. So these were the things. And so the first thing that I told you, that it is, look, if you have OH present, look at this kind of feature. So different kind of compounds that we have seen, alcohol or acid, in all of them you will have this feature, a tongue like feature. Look for the tongue like feature, and then you are sure in that region, if it is there, OH is present. So if it is small like this, appearing like something like this, then you can, this is not OH. But all these are, this is OH, this is OH, these are all, ये सारा OH है, अलग अलग, कोई एस्टर, एस्टर तो नहीं कह रहा हूँ इसमें, हाँ अल्कोहल इसमें और एसिड इन सब में होगा, ठीक है. देन शार्प, very sharp rising negative peak like this, these are usually observed with carbonyls, CO. CO group in organic compounds, ketone, aldehyde, like this. And so these are things that you look for. And I also told you the strongest, highest frequencies are obtained for esters. Uh, Esters frequencies, when you go for esters, they are usually having highest value of CO stretching frequencies, uh, and also the strongest one in terms of intensity. And so now you know this, how to distinguish between sp and sp2 and sp3 carbon. So ये सब अब आपको almost you get habituated to this kind of things, how to identify this. So you have sp2 pure sp sp3 carbon, and in addition to that, if you have ch due to sp2, so that is appears over here. So just below 3000 and slightly above 3000, that is the this is the defining feature of sp carbon and sp2 carbon that we see here, present in different ways. So benzene, hexene, hexane, they have been compared, and you can see so if the number, so you can see this intensity will also depend on how in a given molecule how many such sp2 carbons ch bonds are there. If ch3 sp3 is more ch bonds, so obviously you expect a greater absorption from those bonds. So दोनों चीजें रिलेट होती है. एक तो so there are two things that intensity will depend on two things. One, dipole moment, how strong the dipole is. Two, within the molecule, what is the population, what is relative numbers of such groups appearing in the molecule. So both these things determine your intensity. ठीक है. अगर हम CH2 का प्रोपोर्शन बढ़ा दें CH3 वाले ग्रुप्स का, sp3 का कम होगा, तो फिर हो सकता है कि इंटेंसिटी चेंज हो जाए. सो ये सारी चीज़ें देखनी थी, रिलेटिव प्रोपोर्शन ऑफ हाउ इट अपीयर्स. सो दिस इज व्हाट यू यस. सो क्या क्या मैं कह रहा था, हाँ sp2 कार्बन, ये बता दी. ओके, सो ये सब पहले भी बता चुका हूँ. Then triple bonds, you know, in what cases it will appear. So always if it is asymmetry, double bond, triple bond, जो भी, या simple CC bond भी आप कह रहे हो, वो सब बहुत weak होगा. There is no dipole actually in the, if you are viewing it in isolated, दोनों atom same है, there is no electronegative difference. But if side chain is substituents, something like this, or there is difference between them, then due to some because all of them are continuously undergoing vibrations, so there might be some differences in the electronic distribution, and to some extent you will observe that peak, a very small one. And if it is totally symmetric, it may not be observable, or may be very faint, very very faintly observable in some cases. So it is very weak. We say that CC stretch is very weak, but if it appears, you can easily find out CN stretch. So these are things that we had done. Primary amine, so double bond, then amines NH2. Primary amine always appear as a doublet. Secondary amines a single peak. Okay, so this is what you see. And amides will again show you a doublet, secondary one. So your substitution on N, see, with then you are having only one peak. So see these points. Then we talked about hydrogen bonding. So simple example of so usually the hydrogen bonding leads to weakening of the OH बॉन्ड, ओके, बिकॉज उधर से कोई दूसरा उसको खींच रहा है अपनी तरफ, तो एक जो आइसोलेटेड OH बॉन्ड है वो थोड़ा वीक हो जाएगा। इस तरह से आप सोच सकते हैं, एंड दे विल बी, द एक्सटेंट ऑफ वीकनिंग विल बी डिफरेंट डिपेंडिंग ऑन द डायनेमिक, दिस हाइड्रोजन बॉन्डिंग इज वेरी डायनेमिक, सो बनता टूटता रहता है इन अ सॉल्यूशन, सो दे विल बी लार्ज नंबर ऑफ, सो यू गेट अ ब्रॉड पीक, वेरी ब्रॉड पीक। सो टू एक्सटेंट कितना लोअरिंग होगा और फ्रीक्वेंसी वो सबके लिए अलग अलग होगा। एक साथ कई सारे इसके नेबर्स हैं, एक इधर से एक उधर से खींच रहा है हाइड्रोजन बॉन्डिंग के थ्रू, एंड देयर विल बी सम, so you get a broad whenever you get, so as compared to isolated, if you have, I mean, dilute solution of isopropyl alcohol taken in a suitable solvent, such that you are trying to keep them away from each other, आइसो एक एक मॉलिक्यूल जो आइसोप्रोपाइल अल्कोहल का है उसको अलग अलग आप रखने की कोशिश कर रहे हो, अगर ऐसा कर पाते हो देन यू विल ऑब्जर्व दिस काइंड ऑफ पीक, sharp peak for OH. But the moment you take you have large number of isopropyl alcohol molecules, that is a pure isopropyl alcohol will typically give you this thing, नीचे जो रेड कलर का है, ग्रीन वाला आएगा जब isopropyl alcohol you are preparing a dilute solution. The purpose is to keep the isopropyl molecule away from each other. They should be as far apart as possible so that no hydrogen bonding results. In that case, if you are able to avoid any hydrogen bonding, you will get the green curve. And okay, so this is the idea. So identification of this thing happens like this. Characteristic fundamental frequencies or the stretching wave numbers is this range OH. So this is a summary of the things that we will be dealing with. BH, CN, CO. सो ये हाँ कल हमने CO का भी डिस्कस किया था पिछली क्लास में. So terminals CO and bridging CO. So on bridging you have this kind of thing. It is slightly reduced. Frequency is lowered. The bridging CO will have lower frequency as compared to terminal ones. Okay, so you have frequencies appearing like superoxide, peroxide frequencies. So these are typical frequency that when you coordinated to metal centers, these groups are coordinated, you will typically find these things coming up: superoxide, peroxide, peroxide ligand, SiO, metal Cl bonds are the weakest in that sense. So carbonyls are the one which have been greatly analyzed through IR and Raman spectroscopy, and so the basic thing, highest occupied molecular orbital is having contribution from 3 orbitals, 2s, 2p, and of carbon, and then 2p of oxygen. So it has more of the character of carbon. It is carbon orbitals than the oxygen orbitals, and so it's said to be there lying on this, on carbon. LUMO is also on carbon. So that is the way we understand this structure. So you have, this is another view of the same thing. Okay, and so donations. So this is a scheme that you already know, सब हमने discuss किया था. So there is a donation of electrons through the sigma bond to the metal atom, and then the d metal, the metal having filled d orbitals, they can, if they have suitable symmetry, they can overlap with the pi orbital of the on Cu, and this is how back bonding occurs. So there is, through sigma bonding, it is electron is donated from Cu to metal, the electron density increases on the metal already, if the metal already has some other electron pairs in the d subshell, that may overlap with the, so this is the scheme of bonding that we can discuss. So primarily, first thing that happens is this CO2, the metal, vacant orbital of metal, and then from filled metal orbitals to CO this pi star orbital. Okay, so this is what you will find happening. Okay, so this is a okay, so pi interaction leads to delocalization of electrons. So when from the from which a lone pair which was only feeling the attractive force of one nucleus, that metal's nucleus, now it is delocalized, having experiencing the all these nuclei force of all the nuclei. It is now available throughout, delocalized throughout this orbital. Okay, so empty pi star orbital on this, and this way it is, you are achieving stabilization in this system. Pi acceptor, we call it the pi acceptor ligand. So it is a very good pi acceptor ligand. You should also know that carbon monoxide is this back donation that we are observing, or we can say that the overlap that we are seeing is very good between these two orbitals, the empty pi star and the metal filled orbitals, as compared to PPS3 is another ligand which can also donate and participate as a pi acceptor, but PPS3 is a better sigma donor, and as compared to this carbonyls, PPS3, the triphenyl phosphines, these are better sigma donors. CO is said to be a weak uh, donation, very weak, as I told you, very weak donor to the metal. So the stability in the what carbonyl compounds are known to be stable. The reason is mainly the stabilization comes from this pi interaction. Okay, so that is a major thing. And so you will, so because if there is, so now what will happen in the spectrum में आपको क्या दिखेगा? अगर बैक डोनेशन हो रहा है, if it is effective enough, the because it is going to the pi star orbital, which is anti-bonding in nature, the bond strength, CO bond strength, will be less. So more is the back donation, they will be lowering in the frequency, greater will be lowering in frequencies. So this is the idea that you have to pick up when you analyze the metal carbonyls. So stronger the metal carbonyl bond, the pushing, that means through the pi system there will be more electron density coming into the pi anti-bonding orbital of carbonyl, and so that will, so more electron density comes into the orbital, anti-bonding orbital, bonds will become weaker. So the bond order, so initially in CO you had bond order will so there are two extreme cases when we can analyze. One is that when two electrons are fully donated to metal atom, a formal metal carbon double bond should have been formed. And similarly, CO bond order will also reduce to 2, because anti-bonding, if two electrons come in this, so you have initially carbon monoxide, CO has 3, bond order is 3. Okay, but as soon as anti-bonding orbital starts filling up, the bond order will decrease to 2, if it is like this, the situation is this. So in practice you have somewhere in between the two scenarios, two extreme cases. one with no back bonding, one with complete back bonding. Okay, so something so you have practical thing is observed somewhere in between. So infrared spectroscopy is so pi back bonding के बारे में आपको बहुत अच्छे से जानकारी मिल पाती है. So CO gas absorbs at 2143 cm inverse, and typical metal carbonyl complex will be in this region. And as we discussed in the last class, so you can see here CO 2143 2090. So look at the metal, then so electron density, as as more and more electron density is transferred to the CO, you can see that through the pi back bonding the bonds are becoming weaker. CO stretching frequency is decreasing. What is this? This is the pure CO isolated. You have, if you have only CO gas, it is like this. Combined with manganese, CO6, all are hexa coordinated in octahedral coordination compounds that you see. And gradually from the Mn to titanium, what we are seeing, there is increase in the charge on the, so +1 0 -1 -2. This is the charge on the metal charge on the metal that we are seeing. So from a positive to it is in the Mn, you are having negative -2 charge on the titanium. So that means a large amount of electron density in the metal, it will try to push those electrons to the empty pi star orbital and that will happen. So a large amount of electron density is shifted in this case, and you are getting among these the weakest bond, and so smallest frequency. Whereas in other case the back bonding is here also, but it is not up to that extent in the case of Mn. So these are the things. CO stretching frequency is decreased when it serves as pi acceptor. Well taken. As other pi acceptors is, so okay, so when you substitute some of this CO, suppose these are the examples where चारों तरफ से छः के छः साइड से आपको सिर्फ कार्बोनिल ही थे. Suppose some of these carbonyls are substituted with other ligands and that ligand is also a pi acceptor, then there will be a competition. Okay, so in such cases the CO frequency will decrease depending on the CO frequency. So okay, so what happens that in the competition, if it is able to take up that electron density, then CO frequency is going to increase. ठीक है, कि जितना वीक हो सकता था उसको उतना वीक होने नहीं दिया. ठीक है ना, पहले इलेक्ट्रॉन क्लाउड बहुत ज़्यादा चला जा रहा था. नाउ बिकॉज देयर इज ए कंपटीशन, दूसरी तरफ से पाई एक्सेप्टर एक और लिगेंड है, तो इट विल ट्राई टू हैव दैट शेयर ऑफ इलेक्ट्रॉन्स. पाई सिस्टम में जो शेयर ऑफ इलेक्ट्रॉन है वो उसको लेने की कोशिश करेगा, और ऐसा हो सकता है कि so because it will take up some of those that electrons from the pi system, so the actual electron density in CO will be less due to back donation, and so its frequency, the weakening will be of the bond will be less. So frequency थोड़ा सा जो नॉर्मल आपको एक कंप्लीट इसमें दिख रहा था उससे थोड़ा सा चेंज आएगा. इट विल स्लाइटली इंक्रीज as compared to only when it is having only CO ligand. So donor ligands, so this behavior is opposite to the, if donating ligands other than C. So if sigma donation is increased, then that means, but if the substituted ligand is not able to accept the pi electrons through pi system, that means because donation for the metal has increased, metal पे electron density बढ़ गया, so there is increased electrons in metal, and this increased electron density has to be uh, uh, compensated. It has to be delocalized somehow. It has so that who can accept it? Only CO will be there, so they will be उसके ऊपर और प्रेशर बढ़ गया कि वही सारा इलेक्ट्रॉन मुझे ही लेना पड़ेगा. तो ऐसे केस में पाई स्टार में और ज़्यादा इलेक्ट्रॉन आ जाएंगे, फ्रीक्वेंसी विल डिक्रीज further from a situation we are comparing a situation where only CO is present, and then two situations, one having you have other pi acceptor ligand in the same complex, and having a sigma donor ligand in the same complex. In those situations, so one even having a pi acceptor ligand causes slight increase in the frequency, having a donor ligand in the same complex causes a decrease in the frequency. So this is the idea that you need to learn. So strong sigma donor ligands attached to a metal carbonyl and a formal negative charge on metal carbonyl anion both result in slightly greater CO bond lengths. So lower frequency, so decrease stretching frequency will be there. So so these are terminal ligands that we have seen, all having single uh, one coordinating with one metal only. But there are examples you will find in the books that it can also, one CO can also simultaneously form bonds with two metal centers. So this is your carbon, this is oxygen, and these are the metals. Okay, so these are metals, CO, and 2 to 3 metal atoms. So this in this way. So bridging will what will happen when bridging occurs? In case of bridging, like M2CO, M3CO, which we have shown, there is so increasing the occupation of the pi star orbital as the CO molecule bonds to more metal atoms, more electron density goes into the pi star. Okay, so each of these metal centers will be donating its electron to the orbit, this anti-bonding orbital same carbon. पहले उस CO कार्बन के CO के जो पाई स्टार ऑर्बिटल थे उसमें एक मेटल का इलेक्ट्रॉन डेंसिटी आना था अगर सिंपल MCO होता. नाउ इफ इट इज देयर टू मेटल एटम्स, तो दो मेटल का इलेक्ट्रॉन डेंसिटी जाएगा. If it is three, then three metals ka combined electron density will be added to this uh, 5 star orbital. So you can expect as in gradually as this bridging shows, bridging happens, there will be gradual weakening of the CO bond. ठीक है. So so typically bridging two so when there are two metal atoms bridging, then it is in between the 1715 to 1900, and when we have three atoms bridging, it is 1600 to 1800, like this. So this is the range and the scheme of the things that you have to learn. So MCO, M2CO, and M3CO, gradual weakening of the frequencies. You can also think of, because if CO is considered to be a 2 electron donor neutral ligand, then these 2 electrons are, if it is one metal coordinating with one metal atom, then 2 electrons are donated to one metal. If there is, it is bridging like this, then those 2 electrons of the CO are going into both the metal atoms. So that will be uh, the share is so the share so now it will be acting as 1 electron donor for each of the atoms, metal atoms. ठीक है, सो ये सब चीज़ें हैं जो आप ध्यान दे सकते हैं। और इसी तरह से जब आप 3 पे जाएंगे तो और कम हो जाएगा नंबर ऑफ इलेक्ट्रॉन्स। CO is 2 electron donor for one metal, so the same 2 electrons are now being shared with three metal atoms. Okay, so this is done. Then I told you that you can distinguish between these three things. So it is also possible through spectroscopy we can learn about distinguish between bridging and the terminal ligands. So you see this one is due to the terminal ones, and the bridging ligands appear at lower frequencies. So these are typical values of the, you can find some comparisons in this. So the trend within the group, how it changes, you have these things. Other than that, a very different way of metal carbonyl compound bonding is this scheme, where it is the pi electron cloud of CO overlapping with metal center. This is this is in addition to the one bond which is already, so this is also metal, this is also metal. So this is a sideways side on bonding to the through, similar to just like it interacts with the ethylene electron cloud, double bond electron cloud. Pi electron cloud is donated to the metal. So just like it is acting as a pi donor, just as alkyne and N2 as ligand when you treat. So it is important structural analysis. It is possible. It gives you a lot of ideas if you combine, if you analyze infrared and Raman spectroscopy. And sometimes it is also helpful because the order scale of IR, the vibrations that we record, it is an event happening at the 10 to the power minus 12 is the scale. There's a time, within that time we are capturing the signal. So few picoseconds. Whereas there are some other techniques like NMR that can also give you some idea. But the problem is जो टाइम स्केल है मेजरमेंट का, उसी में वो अगर मूव कर गया तो आपको टाइम एवरेज इन्वायरमेंट अलग नहीं मिलेगा. सो देयर सम एग्जांपल्स व्हेन वी विल डिस्कस एनएमआर, वी विल टॉक अबाउट दैट आल्सो, कि हाउ इन सम केसेस एनएमआर से ज़्यादा आपको आईआर, because it is giving a snapshot of a very short time, and if it able to completely rotate, undergo rotation and something, you will get only time average picture in case of NMR. So sometimes that happens difficulty, so that we'll discuss later when both the things are taken care of. So 5 coordinate system AX5 अगर कोई एक system है, so it can adopt square pyramidal or trigonal bipyramidal geometry. I hope you remember the group theory part. Now if you analyze this, so you can find out the number of modes that may be available. So fundamental vibrational modes. So if you analyze this from the group theory and try to, so if you find out what are the possible vibrations that can happen and find out the symmetry, and then if you do know this group theory point groups, you can further reduce those vibrations into components, into symmetry species by irreducible represent to the corresponding irreducible representation. So there are 5 stretching modes in trigonal bipyramids. Out of that, the symmetry of that is found to be 2 of A prime type, 1 is of A2, prime, and one is E prime. But E, as you know, is doubly degenerate. So this is actually, so E means this is doubly degenerate. So this is how we are counting for 5 stretching modes. 3 are IR active. For IR activity, you need to the change in uh, so uh, so out of these 3, IR active means you need there should be dipole moment change, and whereas for Raman activity you need to have the change in polarizability. So A means almost very highly symmetric vibration. A happens to be just like, remember, s orbitals and kind of things, spherical things having asymmetry. So that vibration is the one which is having highest symmetric vibration, that will be Raman active. Obviously less symmetric ones like A2 is not Raman active. E prime is the doubly degenerate. So this is the bending mode, that degenerate, doubly degenerate that we are talking about is the bending modes of the vibration that can happen. So if it is trigonal bipyramidal, the point is that if the AX5 molecule is having TBP structure, we should get 3 IR bands and 4 Raman. If it is square pyramidal, the same analysis tells you that you should get 4 IR and 5 Raman bands. Okay, so what we actually observe, if you take an example of BRF5, that the 3 IR and 4 Raman bands are observed. So that is it's in consonance with the agreement with the square pyramidal geometry, and which is also expected from Whisper theory. So this is just one example how we can, um, if we have a molecule whose chemical formula is known, we are not sure about the geometry. So in this way, Raman and IR can help you deciding what it is. So we have seen that in case of, we have already seen about CO stretching frequency lying in this region, 1700 से 2100 तक है, and range, so number of CO stretching frequency, range of CO frequency, and number of CO bonds. So you can try to find out, if you know about it, the stretching frequencies and number of CO present, then you can predict the structure. So using group theory and analysis, and involving that analysis in this IR and Raman spectra, you can actually find out this. Okay, so if there is no center of inversion, or a threefold, if they are not related by a center of inversion or a threefold or higher axis of symmetry. So normally what we expect under these conditions, if there is n number of CO ligands, there will be n number of stretching absorption bands. If this is not so, if there is no center of inversion, if there is or a threefold or higher axis of symmetry is not there, then it should be same. No, it straight away corresponds to this number of ligands, number of stretching bands. So stretching absorption band, so it is the IR that we are talking about. Absorption bands का मतलब IR होगा. Raman is not an absorption band. So if it is a bent condition, so imagine OCMCO, if it is a bent condition or a linear, that will have effect on this, because in bent condition you will have twofold. So you will have only two infrared absorptions in this case, uh, because antisymmetric and एंटीसिमेट्रिक वाइब्रेशन दैट विल, वो तो पहले से भी IR एक्टिव था, लेकिन सिमेट्रिक स्ट्रेचिंग विल ऑल्सो बी इन अ बेंट कंडीशन, इवन द सिमेट्रिक vibrations, symmetric stretching is also IR active if it is bent. If it is linear, then symmetric stretching is not IR active. So this is a case in point, that so in this case you have both in a bent molecule, both the symmetric stretching, anti-symmetric stretching, both will be IR active. So this is a correlation if we want to make between the structure of a carbonyl complex and the number of CO stretching bands. This is how we can do this. So starting with the highest symmetry possible, MCO6. MCO6 में number of bands that you observe is only one. If you go for the next lower symmetries, MCO5L, in the same octahedral coordination, but one of the CO has been replaced with L, another ligand. In this case, the point group is different, less symmetry, C4V, and there is so number of bands is expected is 3, but can you think of any isomerism? नहीं, इसमें isomerism no. Okay, so then you have, in case of MCO4L2 trans cis, two things are there. So in case of trans, where you have greater symmetry, only one band is appearing. When the four CO ligands are planar, they are in the same plane, then you have only one band is appearing. Whereas in the cis isomer, you are having cis isomer में आपका symmetry चला गया. So in this case, in a cis isomer, you are having greater number of bands appearing. So जैसे जैसे symmetry कम हो रही है, what you are observing, higher symmetry to lower symmetry for the same number of for the same formula, if the molecular formula is same and we are having two structures, one of the higher symmetry, another one of lower symmetry, पहली चीज जो हमको समझ में आती है, that is there is increase in the number of observed bands in IR spectrum. Okay, so then you go to the MCO3L3. So there will be two isomers, FAC and MER. MER isomer फेशियल, एक फेस पे तीन, सो ऑक्टाहेड्रन के एक फेस पे तीनों आ गए, एल एल एल, एक ट्रायंगल के तीन कोने पे, तो ये फेस एक फेस सारे, देयर आर 6. अब तो ये तो आप जानते हैं ना, ऑक्टाहेड्रल में क्या होता है. Octahedron, the name comes from 8 faces. You have 8 faces, and on the one face, if you have 3 ligands occupying the corners of the triangular faces, that is facial isomer, FAC isomer. And if it is not so, if it is उससे बदल के कुछ और भी दूसरा कुछ होगा उसी फॉर्मूला के साथ, तो वो मरा आइसोमर, ऐसा आप समझ लीजिए. इसको मेरी डायगोनल कहते हैं, कि बीचों बीच जो लाइन है उस पर लाई कर रहा है, मेरी डायगोनल. So that is how, because so this is the meridianal thing. So again, 3 to increasing symmetry with having less number of these things, C2V, C3V. C3V has a less number of bands. So this is a simple correlation that we are getting. Then you have MCO5, MCO5, MCO5 में दो कोऑर्डिनेट MCO5, ओ नहीं नहीं, ये गलत, MCO5 ये नहीं है, 1 2 3 4, ये गलत लिखा है, MCO4 ये एक्चुअली, हाँ ये टाइपिंग मिस्टेक है शिवर एटकिंस में, तो दिस इज MCO4L axial, दिस इज इक्वेटोरियल. सो जो सबसे नीचे यहाँ पे हम देख रहे थे, एक मिनट, हाँ, लेट मी जस्ट क्लियर द स्लाइड्स फर्स्ट. सो यहाँ पे जो हम देख रहे थे, ये प्योर trigonal bipyramidal MCO5. This is a perfect TBP structure, trigonal bipyramidal. D3H is the symmetry, and the number of bands appearing is 2. MCO4L, इसमें दो होगा, एक axial और एक equatorial. This is not correct. Okay, so MCO4L, that is total 5, but 4 of them are CO ligands. So there are two things that you can see. You can put the L over here or over here, either in the axial position. So this is axial ligand, this is equatorial position, so here it is there. So again, if you find out the point group, this is C3V, this is C2V. So number of bands here is yeah, thoda sa C2V, here there are 4 bands. So there are some cases where you have in case of these 3, so there are few things that we have to mention. In this particular case, what we are seeing, C4V. So the if so the cases here, if the fourfold array of CO ligands lies in the same plane as the metal atoms, only 2 bands will be observed. So that is the exclamation, that mark that was given. If they are not in the same plane, fourth array of the CO ligands, then you will get 3 bands, otherwise it will be less than that. So then we are discussing this case of these two cases where you have trans CO ligands are nearly collinear. Cis and trans, look at yeah, trans is this one, you have a trans here. Trans CO ligands are nearly collinear one, so because of that, number of bands will decrease. So it is also the local at the overall symmetry to hai hi. There's one more thing that is important, is the local symmetry of CO. So because overall it is less symmetric, we expect greater number of bands to appear, but we also think that when these two CO molecules are stretching symmetrically outwards, uh, they are on a line. So in that case, there will be no trans CO ligands. If they are collinear, then the expected outcome will be that less than 1 band will be less, because that one is cancelled out when if it is bent, as we discussed previously, slightly bent structure, then you have even the symmetric stretching is having that thing. So local symmetry level concerning this CO ligands is also important. Within the molecule, we also have to look at MCO-CO, that kind of symmetry. So that is linear here. So instead of 2, we should be getting 1 band for this. Just like MCO, we discussed this, already discussed this point in case of, so imagine the case of MCO, CO, and MCO. So in this case we were expecting, in this case we expect only one band, and here we were expecting two bands. So similar situation is arising somehow in this case also. So because they are collinear in these two trans cases, there will be one band less, as as predicted by the overall symmetry of the molecule. We are getting a certain number of bands, but one of them, when we look at the local level, we find that it is with respect to the trans CO ligands, uh, more symmetry if we look at only this part, and that will reduce one band will be less. So, and this in trigonal bipyramidal geometry, again you have threefold array of CO ligands is planar in this particular case only. So again only two bands will be observed if they are planar. So in this case they are planar, and so we expect them to have only two bands. So what we have just learned is, so we have it is the local symmetry that also matters, not just the overall symmetry of the molecule. So these are the things important for which help us draw conclusion about a molecular structure. So just for sake of this, uh, so what is this? What we want to summarize here: highly symmetrical molecules have fewer bonds than CO ligands, and when you have in a linear situation, only one IR band after the plane stretching is observed in CO. So symmetrical stretching leaves the overall electric dipole moment unchanged. And अरे ये कट क्यों जा रहा है? Okay. So when we were discussing this thing, so that's why we were expecting two bands. ध्यान से देखिए, look at this graph. We are getting two bands for terminal CO ligands. It was also expected, depending on the overall symmetry of the molecule, that we should get two bands for bridging CO. But because of this, see this circle, because they are collinear, the two bridging ligands are almost lying on the same line. So one of the vibrations will generate no electric dipole moment, जो कि ओवरऑल पिक्चर देख के लग रहा था कि इसमें होना चाहिए, तो इसीलिए हमें एक बैंड कम नजर आ रहा है. यहाँ पे एक ही बैंड मिल रहा है, दो नहीं मिल रहा है. ठीक है, बिकॉज दे आर कोलिनियर. So this kind of effect is quite observed. So we are looking at the local symmetry within the molecule. Overall symmetry of the molecule, it is a big molecule, right? Two metal atoms combined with cyclopentadienyl ligands, then you have four CO molecules. Overall symmetry is it is highly asymmetric, uh, and we can expect a large number of bands to appear. But we analyze the local, look at the positions of the CO bands and analyze the local symmetry. We find that two CO carbonyls are collinear. Okay, and so we are likely to observe less than what we predicted from, on the basis of overall point group. whatever you can predict, उससे भी कम बैंड हमको मिलेगा. Okay, so this is a classic case of cyclopentane FeCP2CO4. So the two high frequencies terminal CO stretch shows two frequencies on the higher side, and the bridging CO ligands shows only the one peak, because the two bridging ligands are collinear. That's why this is happening. So Raman spectroscopy can be useful in okay, so it is complementary, it gives you complementary information. So what we have discussed, this table and last two slides were devoted only for IR. Okay, ये IR को लेके था कि IR के केस में only for IR spectroscopy, and the same these things can be further analyzed with Raman. Um, so that is complementary, because some of the features that is not observed in IR will be observed in Raman. Linear OCO MCO, the symmetrical stretching, uh, these are always observed strongly in Raman. So this is linear वाले केस में जो IR में नहीं आ रहा था, ये रमन में आएगा, बहुत अच्छे से आएगा. So infrared spectroscopy is also useful in distinguishing MCO, mu2CO or mu3CO. So we have clearly seen that. We have also seen that it is good for finding out the strength of the pi acceptor ligand. We can also talk about, so these are the things. So you have learned so many applications of IR and Raman, mostly IR that we are discussing. So sometimes you can so now you should be able to solve such problems. So this is a complex chromium having 4 CO ligands and 2 triphenyl phosphine ligands. So it has a strong IR absorption and 1889 cm inverse, and 2 other very weak bands in the CO stretching region. So what is the probable structure of the compound for this compound? Here, one thing you should understand, CO stretching frequencies are lower because PPH3 is a good sigma donor and a poor pi acceptor. Better sigma donors, so and poor pi acceptor. So सारा का सारा CO के ऊपर पाई इलेक्ट्रॉन डेंसिटी एक्सेप्ट करने का बहुत बड़ा रिस्पॉन्सिबिलिटी है. सो CO, in order to stabilize the metal, CO has to be take up a huge amount of electron density, and that will weaken the bond. So stretching frequency will be lowered. ठीक है, पहली चीज तो ये. Now you look at the other points. What are the possible isomers? What is the so we can have that it can be cis or trans configuration is possible in these cases. Cis isomers, the 4 CO ligands are in low symmetry C2V, and therefore 4 IR bands should be observed, as we have seen in the previous table. So using the table that will be useful. जो पहले टेबल दिखाया है उसको देख के आप एनालाइज कर सकते हो. अगर C2V सिमेट्री है सिस आइसोमर में, so you are expecting 4 IR bands. But in the trans isomer case, which is a square planar array of 4 CO ligands, D4H, for which only one band in CO stretching region should be observed. So the so it is the second one that we are going for, that it is more likely to be a trans CO arrangement, and a weak band weak bands reflect this thing, small departure from D4H symmetry that is imposed by PPS3 ligands. These ligands, you should remember that these ligands are not points, just point atom or points, right? They are themselves a large one phosphorus connected to three benzene rings. So that is a huge molecule, उसका अपना एक सिमेट्री होगा, सो उसकी वजह से परफेक्टली D4H सिमेट्री नहीं होगा, लगभग लगभग D4H है. So there are some weak bands observed because of that. But so it is more in, so that makes the analysis a little bit difficult, but you can see that it clearly not fitting into C2V. You are not observing four bands, you are observing one strong and plus two very weak bands. So weak bands, appearance of weak bands is due to the PPS3 ligand, which is very bulky. It is itself having a huge three rings, aromatic rings around it. There's two such ligands, so they will slightly distort this as the symmetry is slightly away from D4H. What we, if we simply look at it considering the points, the way so L simple points, if you put it, we find that the D4H symmetry was there in a TVP structure. But considering the nature of bulky ligands like PPS3, there will be small departure, and because of that some new bands may appear, weak bands may, so that is the reason for that. So rest of it, okay, so this is all for today. We'll have two more things to analyze in this case, amine and nitritro, and then we'll done with this. So by tomorrow I will like to finish this part and move to NMR in the next session. You can have another test if you want, अगर आप चाहें तो एक, नहीं तो हम असाइनमेंट दे देंगे. So you will have level 2 of this IR Raman analysis we can do. So I can close this